Welcome back to the deep dive, everybody. Ready to flex those brain muscles? Today, we're all about elegant solutions and clever coding because we're tackling a classic Project Euler problem.
And who doesn't love a good Project Euler challenge?
Right. We're diving headfirst into problem 2 this time. And get this, it involves the famous Fibonacci sequence.
Ah, Fibonacci. Always a crowd pleaser.
For sure. And for this deep dive, we're going with Python as our coding language because, well, Python just makes sense here.
It does, especially when you see how easily it handles what could otherwise be some pretty intense computations. But let's not get ahead of ourselves.
Okay, so, listeners, Project Euler Problem 2. It asks us to find the sum of all the even Fibonacci numbers. But there's a catch. Those numbers have to be less than 4 million.
Sounds deceptively straightforward, doesn't it? Like something you could just, I don't know, brute force your way through.
Brute force. Is that a technical term? Kidding. I think I get what you mean. But for those of us who haven't been living and breathing algorithms, what exactly is brute force in this context?
So imagine this. You tell your computer, hey, little buddy, calculate every single Fibonacci number until you hit that 4 million limit. And then for each one, it's like, is this even? Yes? No. Okay, moving on.
Okay, I can see how that would work. Eventually. But it sounds kind of like, I don't know, using a sledgehammer to crack a peanut.
Exactly. And very, very inefficient, which is where a little bit of number theory swoops in to save the day.
Ooh, number theory. Always a good sign that we're about to get into some really elegant problem solving. Lay it on us.
So the Fibonacci sequence, right? 1, 1, 2, 3, 5, 8, and on it goes. Now, what do we notice about this pattern?
Let me see. 1, 1, 2.
Oh.
Every third number is even.
Bingo! You're catching on quick.
Right.
And this isn't just some happy accident. There is a beautiful mathematical reason why this happened.
Really? Now, you've got to explain this one.
Yeah.
Because I'm looking at this sequence, and I'm not immediately seeing why that pattern exists.
Well, let's think about how we get to each number in the sequence. We add the previous two, right? So when you add an odd number to another odd number.
Yeah. Get an even number.
Precisely. And when you add an even number to an odd number.
You're back to an odd number.
You've got it. And since our Fibonacci sequence kicks off with 2 ones, which are both odd, we're locked into this even, odd, odd, even, odd, odd pattern from the very start.
That's so cool. So what you're saying is, if we're only interested in the even Fibonacci numbers, we don't have to calculate every single one. We can just, skip ahead.
You're getting it. And that's where Python comes in, with its ability to handle those numerical calculations like a pro.
Okay, I'm really starting to see how this is all coming together, but let's get specific. How would we actually implement this in Python? What would that code look like?
Well, we could start by using a loop, right? But not just any loop. We want one that jumps ahead in our sequence. Instead of going one by one, we can directly calculate the even-positioned Fibonacci numbers. This way, we're taking bigger steps, saving ourselves a ton of computation time.
Wow. That's like finding a secret shortcut on your way to the finish line.
Exactly. And that's what's so great about this problem. It really highlights how computational thinking and mathematical insight can work hand in hand. We've gone from a brute force approach, which, let's be honest, would have made our computers sweat a bit,
to an elegant and efficient solution that takes advantage of a beautiful mathematical pattern.
And isn't that a beautiful thing?
It really is. And for our listeners out there who are eager to explore more, here's something to ponder. What other sequences or patterns in mathematics could we use to optimize our code? Happy coding.